Hello and welcome to section 6.6. In this video we'll introduce frames and machines and work on example 1. So on the document you see here we have a frame and a machine. So a frame is designed to not move. Just like a truss, it is pinned. So we have pins at these locations here, 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 and here. The difference between a frame and a truss is a frame has some members that are not two-force members. So for example, this one has a 6 kilonewtons in the middle, so we cannot model AB as a two-force member. Same thing with BC. It has this force, this distributed load, so we can't model this. AC and DC are two-force members. We could slice through those if needed. Machines, a lot of times machines and statics will have pulleys, and these ropes cannot support any forces except for tension, so if needed we can cut through these. However, this member down here, A, B, and then this hook down here, this is not a two-force member because we have a force right here. So everything we learned for trusses applies here. The difference is we can't cut through every single member, so we can only cut through ones that have tension or compression. If we needed to, say, find the forces at B, we could still analyze it at the joint. We could still disassemble it, say, right here at the joint. So you can see how that kind of looks here with this example. Alright, so let's jump into example 1. We're given the following, so this isn't designed to move, so therefore this is a frame. So we have this setup. So let me go over here to our visualizer. So this is what the free body diagram looks like of the entire thing. What you will notice is that we have a whole bunch of external forces. So we have 1, 2, 3, 4, 5 reaction forces. That's 5 things we don't know. So if you remember rigid body equilibrium, we only get 3 equations. So we have way more things than we want to solve. And we ran into this before, and what we would do is we would just kind of ignore some of these. We might say, oh, I'm not worried about AY, I'm not worried about DY, and we could then solve this. But now we're going to leave these alone, and we're actually going to try to solve them. We're going to do that by decoupling these two bars. So we have the yellow bar ABC and the blue bar CD. And so we're going to separate those so that we can solve them. So it'll look like this. And so I've done most of the work here as far as separating it. So we have all the same stuff. The only thing I haven't put in is C. So what happens at C? So if you think about the blue bar, well, it's being pushed down. And so it's going to push down on C. And the reason it can't go down is because this is pushing back on it. So we basically have a normal force here at C. So I can call this the normal at C. You could call it force C, but it's a normal force. So it's perpendicular to that. So just like everything else we've been doing with trusses, we need to reproduce this force over here, opposite direction, same magnitude. That way when I put these two, the blue bar and the yellow bar, back together, it goes away and I maintain my rigid body equilibrium. So we're asked to find AX, AY, BY. Basically it says find the forces at A and find the forces at B. So again, like I said, we can't do it up here. We have too many unknowns. So if I come down here, I have 1, 2, 3, 4 unknowns. So I can't solve this side yet. On this one, I have 1, 2, 3 unknowns. So the strategy here is I'm going to use this blue bar to find the normal at C. This normal is the same as this normal. Once I find it, then I will only have 3 unknowns left over here to find, and then I will solve with the yellow bar. So we're going to start off with bar CD. Let me switch pens here. So bar CD, so we only need to find the normal at C. So I don't want to do forces Y or forces X. Instead, what I'm going to do is I'm going to do moments about D. So we do sum of moments about D. And that will eliminate these from the equation. They won't show up because they can't produce a moment about the point that they're acting at. So we're going to get the 600 newtons. It's going to be acting 1.5 meters away. So it is perpendicular to that bar, so I don't need to do any translation. I don't need to turn it into an XY component, which is kind of nice. It is going to produce a positive moment because it's going to go around that way. The normal at C is going to act 3 meters away. It is going to produce a negative moment. This all has to balance out to 0. And so let me pause the video and I will calculate NC for. Alright, so that is 300 newtons. So we don't need to keep going. We don't need to find dx or dy because they're not part of what we're trying to find. Remember, we're just trying to find ax, ay, and by. So we only needed to find NC so that we could put it over here. So now that we know it, we can just use the yellow bar. So now we're going to work with bar ABC. Alright. So the next thing to do is, so AY and BY are both in the Y direction. So I don't want to start with sum of forces in the Y. AX is in the X direction. We can use the component of the normal here, the X component of it, to find that. So we don't know what that direction is. We never actually specified it. So we know that it is normal to this bar, which means that it is the same angle off the vertical since it's normal. So it'll be 45 degrees, which means that it'll be 45 degrees off the vertical. It gets a normal force. So let's do sum of forces in the X. Assume right is positive, equal to 0. So my forces, I have AX. This 800 newton meters is not a force, so we don't include it. And so we only include the X component of this normal of C. So we're going to have minus NC, and then we're going to have the sine of that 45 degrees because we need the opposite component. We know that this NC is 300 newtons because we found that before. Again, it's the same magnitude, it's just opposite direction as we put it on the other bar. So let me calculate AX for you and I'll be right back. It ends up being 212.1 newtons. So now we can think about what we want to find next. So again, both these are in the Y, so sum of forces in the Y is going to give us an equation with two unknowns. So what we should do instead, let's do moments about A. So AY won't show up and BY will. So we'll do sum of moments. We could also do sum of moments at B and we would find AY instead, so either one is fine. Sum of moments at A, I'll assume right hand rule positive, equal to 0. So our moments, so again AX, AY don't do anything. That 800 newton meters does matter. It is a negative 800 because it is opposite the direction I assumed was positive. So BY will act 2 meters away. It will produce a positive moment. The NC, so the Y component of it, will produce a moment. We neglect the thickness of this bar. If you go back and look at the problem, you'll notice I didn't give you a thickness of it. Actually, we'll just double check that real quick. Yeah, there's no thickness in the bar, just the Y component. So we have that normal at C, and this time we're going to use the, that's going to be, put it in as positive, determine the sense manually. So NC cosine of 45 degrees, it acts 4 meters away, and it will produce a negative moment. Alright, so again, we know that this is 300. Again, just put it in as a positive number, determine our sense manually. So let me find BY, and I will be right back. Alright, and that ends up being 824.3 newtons. So the only thing left to find, so we know AX, we know BY, we know NC, so AY is the last thing to find. So we could do a moment about B, or about C, or sum of forces in the Y. So given the choice, I'll do sum of forces in the Y, because it's a little bit easier. So sorry, I can't quite zoom out enough here. So sum of forces in the Y, going up, equal to 0. So we will have AX, BY, and then the Y component of our normal. So AY will be positive, BY will be positive, and then our normal at C will be negative, and we're going to use the Y component, which in this case is cosine, because we're going from the vertical, cosine of 45 degrees. So we know this is 300, and we found that this was 824.3. So now all we're going to do is solve for AY, and I will be right back with that answer. Alright, and that answer turns out to be negative 612.2. So all the negative means is that as NC pushes down, this bar wants to kind of rotate, so AY has to actually push down to keep the bar from rotating. Alright, if you have any questions, feel free to contact me.